Let's take a look at some special cases of collisions, specifically the various types of collisions known as inelastic and elastic collisions. And then in particular, we'll look at an example of an elastic collision and take a look at a couple of the strategies available when trying to solve such a thing. So in summary, the types of collisions that are out there, most collisions, nearly all collisions, are inelastic collisions. This means that the objects bounce apart somehow and that there is energy lost in that bounce due to energy being transformed into maybe sound or heat or being used to deform the objects. There's also a special class called completely inelastic collisions, which again has to do with energy being lost. That's really what this term elastic has to do with, is it has to do with energy, not really the bounce or whatnot. So an inelastic collision is one where energy is lost, and a completely inelastic collision is not where all the energy is lost, but when the maximum amount of energy is lost and the objects stick together. So this is a case where you would combine the masses together into a total mass times the final velocity. Your right-hand side of the equation typically looks like this. But what I want to focus on mainly in this video is an elastic collision. And an elastic collision means that, of course, momentum is conserved, but the way that the objects bounce, there is no energy lost. And so energy is also conserved, and we have another piece of information to use in our problem solving. Again, just to reaffirm this, whenever you have some sort of a collision, you should be thinking momentum. These ideas always, always, always go together. The only time that you are going to add in ideas of energy conservation during a collision is when you know for sure that it is an elastic collision. Let's take a look at this somewhat silly situation here where we have a meatball traveling to the right, let's say, at 5 meters per second. This is our 2 kilogram meatball. And it's going to collide with another meatball, slightly bigger, also traveling at 5 meters per second, but in the opposite direction. So we'll make that a -5. And what we're being told here is that it's an elastic collision. Well, first of all, whether it's elastic or inelastic, we can always write the ideas based on momentum conservation, that the momentum before has to equal the momentum afterwards. So we could state that 2 times 5 plus 3 times -5 would equal, okay, now normally we have one of the velocities. In this case, I don't know either one of the velocities, so I'm just going to call them V1 and V2 in my setup. So the 2 kilogram object is moving at some speed, and the 3 kilogram object is moving at some speed. All right, so I have two unknowns. That means I'm going to have another equation in order to solve this. But the fact that I know it's elastic means that energy is also conserved. And specifically, it's kinetic energy that is conserved here. So I can say that the kinetic energy that I start with must equal the kinetic energy that I end with. And of course, kinetic energy is 1/2 mv squared. So we can say that 1/2 times 2 times 5 squared, that's a 5, I swear, plus 3, I forgot my 1/2, 1/2 times 3 times, again, 5 squared is equal to 1/2 times 2 times this unknown v squared plus 1/2 times 3 times v2 squared. Now it looks a little messy there, but we can do some simplifying. This comes out to be just 25, and this comes out to be, let's see, 25 over, I better do this in a couple steps here. So this is 25, this is 25, divided by 2 is 12.5. I should have done this in advance here. It looks like 37.5. And then this is v1 squared plus 1.5 v2 squared. Now, kind of ugly equations, but we could solve this. We could solve one of these equations for maybe v1, plug it into the other equation, and solve for V2 that way. We could graph these two equations and look for an intersection point. Okay, but there would be a way for us to find the speeds. If you want to try it out, the answer does come out to be -7 meters per second for V1 and 3 meters per second, +3 for V2.